Hello everyone. Today we are going to analyze this beam using moment distribution method. Before analyzing, let's see the beam one time. In this beam, there are three spans: span AB, span BC, and span CD. In the span AB, there is a point load 20 kN acting on the center. In the span BC, there is a point load 25 kN acting at 2 meter from the support B. In the span CD, we are having UDL 12 kN per meter acting for the full span. In the point A and in the point D, there are fixed supports. In the point B and in the point C, there are hinged supports. The moment of inertia for the span AB is 2I. For the span BC, it is 1.5I. For the span CD, it is 0.8I. Span AB is 4 meter long, span BC is 5 meter long, and the span CD is 4 meter long. In this beam, we have to calculate 6 moments. In the fixed support, there will be a moment. So, in the point A and in the point D, we are having moments. In the point A, we are having the moment MAB, and in the point D, we are having the moment MDC. In the joints, there will be two moments. In the joint B, we are having two moments MBA and MBC. Also, in the joint C, we are having two moments MCB and MCD. So, totally we have to find 6 moments. Also, we have to calculate 4 vertical reactions RA, RB, RC and RD. Now, let us make the fixed end moments. For making the fixed end moments, we have to assume every span as a separate fixed beam. First, let us take the span AB and assume that it is a separate fixed beam. Now, let's see the formulas to calculate the fixed end moments. In this table, you can see some of the important fixed end moment formulas for the different type of loadings. In the span AB, there is a point load acting on the center. So we have to select this condition. The formulas are minus WL upon 8 and positive WL upon 8. In the span BC, there is a point load. That point load is not acting on the center. So we have to select this condition. The formulas are minus WAB square upon L square and positive WA square B upon L square. In the span CD, we are having UDL acting for the full span. So we have to select this condition. The formulas are minus WL square upon 12 and positive WL square upon 12. Now let us apply those formulas and find out the fixed end moments. In the span AB, we are having a point load. This point load is acting in the center. We have already seen the fixed end moment formulas minus WL upon 8 and positive WL upon 8. MFAB will be negative because it is acting in the anticlockwise direction. MFAB will be positive because it is acting in the clockwise direction. Let us apply the values inside the formulas. W is 20, L is 4. After calculations, we are getting MFAB is equal to minus 10 kN meter and MFBA is equal to 10 kN meter. Now let us calculate the fixed end moments in the span BC. In the span BC, there is a point load. This point load is not acting on the center. We already saw the formulas for the fixed end moments minus WAB square upon L square and positive WA square B upon L square. Let us apply the values inside the formulas. W is 25, A is 2, B is 3, L is 5. After calculations, we are getting M of BC is equal to minus 18 kN meter and M of CB is equal to 12 kN meter. Now let us make the fixed end moments in the span CD. In the span CD, we are having UDL acting for the full span. We already saw the formulas for the fixed end moments minus WL square upon 12 and positive WL square upon 12. Let's apply the values inside the formulas. W is 12 and L is 4. After the calculations, we are getting M of CD is equal to minus 16 kN meter and M of BC is equal to 16 kN meter. In the moment distribution method, we have to find the distribution factor. We have to find the distribution factor only on the joints because in the ends we can easily say the distribution factors. In the fixed ends, the distribution factor will be 0. In this beam, we are having two fixed ends. In the point A and in the point D, we are having the fixed ends. So, in these ends, the distribution factor will be 0. So, the distribution factor for AB and DC will be 0. In this case, we have to find the distribution factor only in the joints. In this beam, there are two joints, joint B and joint C. In these two joints only, we have to find the distribution factor. To find the distribution factor, we have to calculate the stiffness. Let's see the formulas to calculate the stiffness at the joints. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged or with roller support, the formula is 3EI upon L. If the fair end is continuous, the formula is 4EI upon L. Now let's apply these formulas and find the stiffness. From the joint B, we have to calculate two stiffness values for BA and for BC. First, let us calculate for BA. For that, from the joint B, we have to look at the point A. In the point A, we are having a fixed support. If the fair end is fixed, the formula is 4EI upon L. Here, the moment of inertia is 2I. So, instead of I, we have to apply 2I. Length of AB is 4 meter. Let us apply that. Finally, for stiffness of BA, we are getting 2EI. Now, let us calculate the stiffness for BC. For that, from the joint B, we have to look at the point C. The point C is continuous because after the point C, we are having the span CD. If the fair end is continuous, the formula is 4EI upon L. For BC, the moment of inertia is 1.5I. So instead of I, we have to apply 1.5I in the formula. For BC, the length is 5 meter. Let us apply that. Finally, for the stiffness of BC, we are getting 1.2EI. Now let us calculate the stiffness values in the joint C. First, let us calculate for CB. For that, from the joint C, we have to look at the point B. The point B is continuous because after the point B, we are having the span AB. If the fair end is continuous, the formula for stiffness is 4EI upon L. For CB, the moment of inertia is 1.5I. So instead of I, we have to apply 1.5I. The length of CB is equal to 5 meter. Let us apply that. Finally, the stiffness for CB, we are getting 1.2 EI. Now, let us calculate the stiffness for CD. For that, from the joint C, we have to look at the point D. In the point D, we are having a fixed support. If the fair end is fixed, the formula is 4EI upon L. Here, the moment of inertia is 0.8 I. So, instead of I, we have to apply 0.8 I. Length of CD is equal to 4 meter. Let us apply that. Finally, the stiffness for CD, we are getting 0.8 EI. Now, let us calculate sigma K, that is summation of the stiffness. In the joint B, there are two stiffness values. When we add them, we are getting 3.2 EI. In the joint C also, there are two stiffness values. When we add them, we are getting 2 EI. Now let's calculate the distribution factor. The formula is K upon sigma K. For BA, K is 2 EI, sigma K is 3.2 EI. When we apply inside this formula, we are getting 0.625. For BC, K is 1.2 EI, sigma K is 3.2 EI. When we apply inside the formula, we are getting 0.375. For CB, K is 1.2 EI, sigma K is 2 EI. When we apply inside the formula, we are getting 0.6. For CD, K is 0.8 EI, sigma K is 2 EI. When we apply inside the formula, we are getting 0.4. Now, let us start making the moment distribution table. In the table, first let us enter all of the members. Then let us enter the distribution factor values. For AB and for DC, the distribution factor is 0 because in the points A and D, we are having fixed ends. In the joints B and C, we have calculated the distribution factor values. Let us enter them. Then let us enter the fixed end moments. Now let us make the first distribution. The distribution can be done only in the joints. First, let us make the distribution in the joint B. In the joint B, we are having the members BA and BC. For them, the fixed end moments are 10 and minus 18. For making the distribution, we have to add these two fixed end moments. Then we have to multiply with the distribution factors. First, let us do the distribution for BA. For that, we have to add these two values and then multiply with the distribution factor at BA. When we do that, we are getting a negative value. When we make the distribution, if we get negative value, we have to enter inside the table as positive, and if we get a positive value, we have to enter inside the table as negative. Right now, we have got a negative value, so we are entering inside the table as positive. Now, let us do the distribution for BC. For that, we have to add these two values, then multiply with the distribution factor at BC. When we do that, here also we are getting negative value, so we are entering inside the table as positive. Now let us do the distribution in the joint C. In the joint C, the members are CB and CD. For them, the fixed end moments are 12 and minus 16. In the joint C, first let us make the distribution for CB. For that, we have to add these two fixed end moments, then multiply with the distribution factor at CB. When we do that, we are getting a negative value, so we are entering inside the table as positive. Now, let us do the distribution for CD. For that, we have to add these two values, then multiply with the distribution factor at CD. When we do that, here also we are getting a negative value, so we are entering inside the table as positive. Now let us make the carryover. The carryover should be done in every span. First, let us do the carryover in the span AB. In the span AB, there are two movements, MAB and MBA. From AB, half of the movement will go to BA. From BA, half of the movement will go to AB. First, let us do the carryover from AB to BA. For AB, there is no distribution, so we cannot make the carryover from AB to BA. Now, let us make the carryover from BA to AB. In BA, the distribution is 5. 5 upon 2, we will get 2.5. Now, let us do the carryover in the span BC. From BC, half of the movement will go to CB, and from CB, half of the movement will go to BC. For BC, the distribution is 3. 3 upon 2, we will get 1.5. For CB, the distribution is 2.4. 2.4 upon 2, we will get 1.2. Now, let us do the carryover in the span CD. From CD, half of the movement will go to DC, and from DC, half of the movement will go to CD. 1.6 upon 2, we will get 0.8. For DC, there is no distribution, so we cannot make the carryover from DC to CD. Now, let us make the second distribution. Now, under the joint B, there is only one value. For BC, we have 1.2. For BA, there is no value. So now we can easily make the distribution. First, let us make the distribution for BA. For that, we have to multiply this value with the distribution factor. When we do that, we are getting positive value. So we are entering inside the table as negative. Now let us do the distribution for BC. For that, we have to multiply this value with the distribution factor at BC. When we do that, here also we are getting a positive value. So we are entering inside the table as negative. Now let us make the second distribution in the joint C. In the joint C also, now we are having only one value. For CB, we have 1.5. For CD, there is no value. First, let us make the distribution for CB. For that, we have to multiply this value with the distribution factor at CB. When we do that, we are getting a positive value. So, we are entering inside the table as negative. Now, let us do the distribution for CD. For that, we have to multiply this value with the distribution factor at CD. When we do that, here also we are getting a positive value, so we are entering inside the table as negative. Now let us make the carryover. First, let us make the carryover between AB and BA. For AB, there is no distribution, so we cannot make the carryover. For BA, we have minus 0.75. Minus 0.75 upon 2, we will get minus 0.375. Now let us make the carryover between BC and CB. Minus 0.45 upon 2, we will get minus 0.225. Minus 0.9 upon 2, we will get minus 0.45. Now let us make the carryover between CD and DC. Minus 0.6 upon 2, we will get minus 0.3. For DC, there is no distribution, so we cannot make the carryover to CD. Now let us make the third distribution. First, let us make in the joint B. In the joint B, we are having only one value. For BC, we are having minus 0.45. So we have to multiply this minus 0.45 with the distribution factors to get the distribution. Both of the values are negative, so we are entering inside the table as positive. Now let us make the third distribution in the joint C. In the joint C also, there is only one value. For CB, we are having minus 0.225. For making the distribution, we have to multiply this value with the distribution factors. When we do that, we are getting negative values, so we are entering inside the table as positive. Now let us make the carryover. The carryover should be done in the same way we did in the previous steps. We have to divide these values by 2. After dividing, we will get these. In the same way, we can do more distribution and carryover until we are getting smaller values. I have done up to the 5th distribution. I have stopped in the 5th distribution because in the 5th distribution I am getting very smaller values. You can see that I am getting very smaller values 0.009, 0.007, etc. So I am stopping in the 5th distribution. In the last distribution, we have to give the carryover to the fixed ends. In the point A and the point D, we are having fixed supports. So from BA, carryover should be given to AB. Also from CD, carryover should be given to DC. We should not give the carryover to any other members. Only we have to give the carryover to the fixed supports. Now we can add the values and find out the final moments. We have to add the values from the fixed end moments. After adding all of the values, we are getting the final moments. In this analysis, we have calculated all of the moments. For MAB, we are getting a negative value. That means MAB is acting in the anticlockwise direction. In the point B, we are having two moments. For MBA, we are getting positive value because it is acting in the clockwise direction. For MBC, we are getting negative value because it is acting in the anticlockwise direction. In the point C also, we are having two moments. For MCB, we are getting a positive value because it is acting in the clockwise direction. For MCD, we are getting a negative value because it is acting in the anticlockwise direction. Finally, for MDC, we are getting a positive value because it is acting in the clockwise direction. Now, let us calculate the reactions. First, let us take the span AB and calculate the reactions. In the span AB, there are two movements, MAB, which is acting in the anticlockwise direction, and MBA, which is acting in the clockwise direction. In this span, first I am going to calculate RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. The vertical reaction RA is acting towards the point B in the clockwise direction. So it is positive and the distance is 4 meter. So for RA, the point load 20 kN is acting towards the point B in the anticlockwise direction. So it will be negative and the distance is 2 meter. So 20 into 2. Then there are two movements. 7.75 moment is acting in the anticlockwise direction, so it will be negative. 14.5 moment is acting in the clockwise direction, so it will be positive. Finally, for RA, we are getting 8.31 kN. Now, using the rule, summation of vertical forces is equal to 0, we can calculate RV1. In this span, there are three forces. RA and RB1 are acting upwards, so both are positive. Point load 20 kN is acting downwards, so it is negative. We already know the value of RA, let us apply that. In this way, we can get RB1, which is equal to 11.69 kilonewton. Now, let us calculate the reactions in the span BC. In the span BC, there are two moments, MBC, which is acting in the anticlockwise direction, and MCB, which is acting in the clockwise direction. In this span, first I am going to calculate RB2. For that, I am going to take moment about C. The vertical reaction RB2 is acting towards the point C in the clockwise direction, so it will be positive and the distance is 5. So 5 RB2. The point load 25 kilonewton is acting towards the point C in the anticlockwise direction, so it will be negative and the distance is 3 meter. So minus 25 into 3. Then we are having two movements. 14.5 is acting in the anticlockwise direction, so it will be negative. 14.94 is acting in the clockwise direction, so it will be positive. Finally, we are getting RB2 is equal to 14.91 kilonewton. By applying the rule, summation of vertical forces is equal to 0, we can calculate RC1, which is equal to 10.09 kilonewton. Now, let us calculate the reactions in the span CD. In the span CD, there are two movements, MCD, which is acting in the anticlockwise direction, and MDC, which is acting in the clockwise direction. In this span, first I am going to calculate RC2. For that, I am going to take moment about D. The vertical reaction RC2 is acting towards the point D in the clockwise direction, so it will be positive and the distance is 4 meter, so 4 RC2. The UDL 12 kN per meter is acting in the anticlockwise direction towards the point D, so it will be negative and the distance is 4 meter. When the UDL comes, we have to multiply with the distance and distance by 2. So 4 into 4 by 2. Then we are having two movements. 14.94 is acting in the anticlockwise direction, so it will be negative. 16.53 is acting in the clockwise direction, so it will be positive. Finally, we are getting RC2, which is equal to 23.6 kilonewton. Using the rule, summation of vertical forces is equal to 0, we can calculate RD, which is equal to 24.4 kilonewton. Now, let us add RB1 and RB2. After adding, we are getting RB, which is equal to 26.6 kilonewton. Also, let us add RC1 and RC2. After adding, we are getting RC, which is equal to 33.69 kilonewton. Now we are going to draw the shear force diagram. I am going to calculate the shear force values from the point A and towards the point D. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. You can see the shear force values. Using the values, we can draw the diagram. Now we are going to draw the bending moment diagram. For drawing the bending moment diagram, first we have to make the free moment diagram, then end moment diagram. Finally, we have to combine both of them to get the bending moment diagram. For the free moment diagram, we have to assume every span as a separated simply supported beam. First, let us take the span AB. In the span AB, a point load 20 kN is acting on the center. If a point load is acting on the center, the bending moment formula in the simply supported beam is WL upon 4. Here W is 20, L is 4. When we apply inside the formula, we are getting 20 kN meter. In the simply supported beam, if the point load is not acting on the center, the formula to calculate the maximum bending moment is WAB upon L. Here W is 25, A is 2, B is 3, L is 5. When we apply inside the formula, we are getting 30 kN meter. In the simply supported beam, if the UDL is acting for the full span, the formula to calculate maximum bending moment is WL square upon 8. Here W is 12, L is 4. When we apply inside the formula, we are getting 24 kilonewton meter. Using these three values, we can draw the free movement diagram. Now let's see how to draw end moment diagram. For drawing the end moment diagram, we have to see the direction of the curves. First, we have to arrange these movements in the curves. For MAB, we are having a negative value because it is acting in the anti-clockwise direction. So, in the point A, we have to make an anti-clockwise curve towards the point B. For MBA, we have a positive value. That means it is acting in the clockwise direction. So, from the point B towards the point A, we have to make a clockwise curve. For MBC, we are having negative value. That means it is acting in the anti-clockwise direction. So from the point B towards the point C, we have to make an anti-clockwise curve. In the same way, we have to make the curves in the point C and in the point D. Then we have to see the direction of the curves. All of the curves are indicating upwards. That means the end moment diagram comes above this line. Finally, we can connect the values and make the end moment diagram. If the end moment diagram comes below this line, that will be positive. If it comes above the line, that will be negative. Right now, all of the points are coming above this line, so it is negative. Now, let us combine the free moment diagram and end moment diagram and make a bending moment diagram. Here you can see that I have combined both of the diagrams. If you are very experienced, there is no need to make the end moment diagram and free moment diagram. We can directly make the bending moment diagram. Wherever the free moment diagram and end moment diagram are alone without mingling with each other, we can mark the values. Here the end moment diagram, here free moment diagram, end moment diagram, free moment diagram, end moment diagram, free moment diagram, finally end moment diagram. Wherever they are together, we are not marking anything, we just keep the space empty. Now we are going to end this session. Thank you for watching this video.